I also posted another homework. It'll be due on Monday if Trayton doesn't get a touchdown. If he does, it's due Wednesday. Okay? So everyone's got to go to the game, I guess. No, it's due Wednesday. Okay, so you got a week. Another cool thing, we don't have a quiz this week. Don't worry about that. We'll have a quiz end of next week. That'll be over the homework stuff, which will be over torsion and all of that stuff. So you get an off week, bye week on the quizzes this week, okay? Any questions on the homework? Due today, right? Okay. Is there homework due today? Oh, yeah. Monday? What? No, you're wrong class, man. I'm in the wrong class.
You just assigned a homework. The last homework was due last Friday.
Yes. Okay. Sorry, I am getting this class mixed up with my other class. Yes, 24th. That was this one. So now I posted this guy here. Okay. We have columns and we have torsion. Okay. And we'll have a quiz next Friday or end of next week over that material. Okay. All right. We're going to continue with our example problem. Okay. We went through this very long. You guys were super excited about this derivation for shear stress, right, in a shaft due to torsion. We're talking about long, slender members, circular or hollow in cross-section, so pipes or solid rods. Okay. In this example, we have a hollow stainless steel shaft or pipe, essentially made out of stainless steel. They gave us our outside diameter and our thickness of our walls of our pipe. And they also told us that the maximum allowable shear stress of that material was 100 megapascals, right, or newtons per millimeter squared. And based on that information, they wanted us to determine what is the maximum torque that could be applied to the shaft and the angular deflection at the max torque if the rod was 1.75 meters long. So we went through and figured out what our max torque was, starting with this maximum shear stress, right, is the max torque times the radius, the maximum radius, because as we go back to our derivation, right, under an imposed torque on a shaft, our shear stress varies from 0 at the center to its maximum at the outside radius, right? So our max torque times this max radius divided by this stiffness, torsional stiffness, we call it the polar moment of inertia, or J, gives us our maximum shear stress, right? Tau max is T times C over J. Well, we rearranged it and got our maximum torque related to our maximum stress. In this case, it was an allowable stress. Making sure it followed all of our units, and we get a maximum torque that can be applied to this pipe at 830 Newton meters, right? Second question they asked was, what is the angular deflection at the max torque if the rod was 1.75 meters long? Well, no surprises here. We've got our rotational force rotation relationship, right, that we derived, essentially saying the angular deflection equals the torque times the length divided by the shear modulus times the polar moment of inertia. Well, we're given everything here, so that makes this really easy. 829, 980. Remember, consistent units. I'm using newtons and millimeters. All right, 86 gigapascals, that's 86,000 megapascals. Megapascal is a newton per millimeter squared. And our polar moment of inertia we calculated was 174,296 millimeters to the fourth. With a phi of 0.097 radians. If you went through and walked through all this, all of our units cancel, so this is a unitless value. It has a unitless value that has a unit, but it's in radians, okay? Means phi is 0.97 radians. If we multiply that by 180 degrees per pi radians, there are 360 degrees or 2 pi radians in a complete circle. So there's 1 pi radians per 180 degrees. So if we want to convert this to degrees, what does that mean? Well, if we had, let's pretend this thing is, oh, here we go with this one thing. Ah, yes.
Are you gonna ask that we convert it to degrees?
No, I would just follow the units. Like in the quizzes, it'll say blank radians, right? You give it to what they would like to see it in. And then the homework too, it'll ask in radians or degrees. So if this was our pipe, right? And we twisted on the end of it with 830 Newton meters, okay? And this pipe was 1.75 meters long, okay? We put that torque on there. The end, right? If one end was fixed, the end that was allowed to rotate, the degrees, right? If this was start and this was finish, right? That pipe is going to distort 5.5 degrees, 5.5 degrees. It's going to rotate at the end, right? And that linearly changes from the point where it's fixed out to the end, right? It's like half that distance, you're gonna get half that rotation, which if you plugged it in, oh, I'm loving this already. If you plugged it in right here, okay, you're gonna get half that rotation, right? Half the length, half the rotation. Half the torque, half the rotation. So, okay, I'm gonna keep this ready. Any questions on that example? No? All right, we're gonna get into one where you gotta do a little bit more thinking. We're gonna have to devise some free body diagrams, okay? So we can compute what the internal torque is, because at this point we're going to just be provided with external torque. So in this example, we have a 2-segment shaft, and it's used to transmit power at constant speed through the pulleys shown in the figure here. Okay? Power is input to the shaft through the pulley at B, okay? And it's given, that torque is 260 Newton meters. And the torque is taken out at A and C, okay? A at 90 Newton meters and C at 170 Newton meters. The external torques act in the directions indicated. Both shaft segments are made of phosphor bronze. Okay, it has a shear modulus of 42 gigapascals. And both segments are solid shafts. They say segment 1 has a diameter of 25 millimeters, and it gives us our length. They also give the diameter and the length of segment 2. And they want us to determine the rotation angle of pulley C relative to pulley A. Right? Rotation angle of pulley C relative to pulley A. Well, if we assume, right, that A is our reference, right? It's relative to A. So if we fixed A, and then we really want to know how far it rotates at C, we're really trying to find the rotation, right? Rotation displacement is our phi. We want to find phi relative of C relative to A, right? So as you can imagine, we're going to be using our rotation is torque times length divided by the shear modulus times the polar moment of inertia equation, right? But in order for that to work, we need to know what the length, the shear modulus, polar moment of inertia. Well, all of that's based on dimensional and material properties. Those are all given to us. One last thing that's in that equation, though, is torque, right? We've got phi, or rotation, torque times length, G times J, right? Well, we're starting on this end, and we want to know how far does C rotate relative to A, we're going to want to start on one end, right, and work our way over and see how this rotates. I also, on a tangent, I was like, well, when would this system really happen? Well, check this shit out. This is like 1800s textile mill, okay? Back in the day when they had big steam engines, right? They ran big shafts along the ceiling, okay? Back to the whatever the source of the rotation is, right? The big steam engine. And then each of these big pulleys would come down, which we're going to talk about gear ratios here in a little bit. But they'd run down with big belts that would run all of these sewing machines, right? Or mills, right? Pretty badass. I think that's sick. Industrial Revolution. Okay, so that's what we have, right? We've got a motor driving the shaft, and then we've got these sewing machines drawing off of that shaft, that torque, right? Which would essentially be energy if it's rotating. So, let's start with an overall free body diagram. Or an overall equilibrium check. Well, if we look at the diagram or the figure here, right, we've got a coordinate system. It says x is positive to the right, y is positive upwards. So if we sum moments at A about the x-axis, right? For torque problems, right, torque is a moment about the longitudinal axis. So in this case, the torque direction is along our x-axis. So if we sum moments about that x-axis, and we set that equal to 0, we're going to have torque at A, right? With the right-hand rule, thumb is pointing to the right, which is along the positive x-axis. So we've got torque at A. Torque at B is in the opposite direction, right? It's running in the opposite direction. And then we finally have a torque at C. If we input those values, we have 90 Newton meters minus 260 plus 170. Well, that checks out, right? Just kind of overall check, making sure that the equilibrium is satisfied and this thing isn't rotating. So now let's look at our internal torques, right? We already know we really ultimately want to be using this equation, right? Which our rotational deformation is a function of the internal torque in the shaft, right? So we got TL over GJ. Well, we need to know what that internal torque is. So I'm going to look at these internal torques by cutting this system in areas that reveal the internal torques of the two shafts. So I'm going to choose to cut out pulley A. If I cut out pulley A, right, if we cut out the end, kind of like we see here, we cut that out, draw a free body diagram. Okay, this is at A. We're going to have the torque applied at A, right? Torque applied at A is going to be acting on this segment. Well, we're also going to have the torque in the shaft. And this is positive X direction. Well, if we do what we did above and we sum moments about A, knowing they have to equal to 0, I get TA plus T1 has to equal 0, right? both acting in the positive x direction. So we've got TA plus T1 must equal 0. Well, that means that TA equals minus T1. What does that mean? Well, that means that the arrow I showed is opposite, right? Which makes sense. We got to have equilibrium, so we're going to have opposite, equal and opposite forces. So if we've got torque running in one direction, the internal torque in the shaft has to be running in the other direction to maintain that equilibrium, right? So TA equals minus T1. So what's that say? Well, that means T1 equals negative 90 Newton meters. Right? That means T1 is actually acting in the other direction, right? And our sign convention also says that that's a negative because it's acting towards the face, right? Outward normal is positive. So we have 90 Newton meters. Well, that's our internal torque for shaft 1. We also want the internal torque of shaft 2, right? We're going to be working our way across this to figure out what is our angular deflection, right? How far did this thing rotate as we applied torque to it? So we need both the internal torque, so I'm going to cut it right here. You could cut it right there if you'd like to, okay? This seems a bit simpler to me. One external force, one internal force. So I'm going to cut out pulley C. Take pulley C out. Okay. So if I drew a free body diagram of that, we're going to have the pulley at C, right? Looks something like this. We're going to have the applied torque at C, right? T sub C. It's acting in the right-hand direction based on the right-hand rule. And have positive x to the right. I'm going to put T2 in the opposite direction. It's just a guess. We're going to confirm that with our equilibrium check. Right. I guess something to note here that can be confusing is sign convention for torques, right? Outward normal is positive. We've talked about that. But in this case, even though this is a positive internal torque, right? When we are summing moments, the directions we assume as positive or negative are relative to these vector directions, right? So if I'm assuming x is positive to the right, T sub C is positive, but T2 is actually negative, right? It's acting in the opposite direction from the assumed coordinate axis. But T2 is considered a positive torque because it is outward normal from the face of the shaft. Okay? Try not to make that slip you up a little bit. So what does that mean? Well, that means TC equals T2. Or T2 equals 170 Newton meters. So if we looked at a torque diagram, which will be helpful for the quiz next week. If we looked at a torque diagram, which is essentially looking at how the torque varies as we go from one end of the shaft to the other. So if we start at A, work our way to B, and then to C. right? Between A and B, we have shaft 1, which is where, this is where our sign convention comes in, right? When we do equilibrium, our signs are based on the axis that we're assuming. When we do a torque diagram, that's when we use the sign convention for the torques. So in this case, right, T1 was negative 90 Newton meters. What does that mean? Well, that means T1 is actually in the opposite direction. So now if we look at the torque sign convention, right, this arrow is facing towards the face of the shaft. So that's actually a negative torque, right? A negative, in this case, negative 90 Newton meters between A and B. It's going to be constant. There's no external forces acting on this. So when we get applied torque at A, it's going to go in the shaft, and that's what the shaft's going to see all the way until it gets acted on by an external force again, right? So from A to B, it's constant. Well, based on our free body diagram at C, in this case, T2, we assumed it was in the right direction. So it's an outward normal from the face of the shaft. Outward normal from the face of the shaft says it's positive. It's positive. Its magnitude is 170 Newton meters. So it's going to go way up here. So I'll tell you for the quiz, you will have something very similar to this, where you'll have more segments, but you would essentially be able to develop a diagram that depicts what's the internal torque as we move across this series of pulleys and applied forces. Okay? Well, now that we have our applied, or our internal torques, we can go back and utilize this deflection equation. Essentially, we have to develop some additional variables there, right? They don't explicitly give us the polar moment of inertia. So we need to figure that out. So now we have our force displacement equation. In this case, it's torque rotation relationship. Well, that requires this polar moment of inertia. Well, if we look at shaft 1, right, these are both solid shafts. So our polar moment of inertia, as I gave in the notes, is pi over 32 d to the 4th equals pi over 32 times 25 millimeters to the 4th, or 38,350 millimeters to the 4th. If we look at J2, same thing. Pi over 32 because it's a solid shaft. Its diameter is 30 millimeters, so we get 79,522 millimeters to the 4th. So now we have our J1 and J2, right? Polar moments of inertia. So now if we look back at our equation, we're provided with the length. Whoa. Someone wasn't watching. It's a J. Now we have our polar moment of inertia. They gave us our shear modulus. It's the same material throughout. Okay. We have our internal torques for each of our two shafts. We can then figure out how much each of our shaft is going to rotate, okay, from one end to the other based on that applied internal torque. So now we just get to write it all out. T1, L1, G1, J1. This is where units become incredibly important. Oh, I'm gonna do this. Whoops. This should be 42,000 newtons per millimeter squared, right? That's 42 gigapascals. Our J1 is 38,350 millimeters to the fourth. Well, if we work through all of this, all the units cancel. We get radians. We get negative, right? We had negative 90. 1.676 times 10 to the negative third radians, right? Just chugging along, inputting all of the variables. We go back and we look at the deflection of rod 2, L2, G2, J2. Well, this has a positive internal torque, so now we have 170 Newton meters. It has a length of 900 millimeters or 0.9 meters. We've got 1,000 millimeters per meter. 42,000 newtons per millimeter squared. Finally, our J2 is 79,522. And we get a positive 4.581 times 10 to the negative third radians. Pretty good answers there, right? We've got now the rotation of shaft 1 between points A and B, and shaft 2 between points B and C. We go back to the problem statement. They asked us, what is the rotation of C relative to A? So we got to stop and look at, if A was fixed, right, how far has pulley C rotated? So if we start at A and work our way across, okay, we start at A, work our way across, we're going to have this shaft, right? This solid shaft. It's going to change diameter. But if we start with this solid shaft, and we make a mark on the top of this shaft, we make a mark on the top of the shaft at A, okay? And it's going to have an internal torque in it that's going to start rotating it. Going to start rotating it to the right. Right, T1. If we cut a section through this shaft, and we were looking at the end of the shaft, the pulley A was behind it. Okay, we know T1 being negative, it's acting in the direction of the shaft, so it's rotating it clockwise. We know that it's going to rotate it clockwise this 1.676 radians. Right, so we're going to rotate over this phi1, right? This rotation angle 1 as we go from A to B. So we're going to run over, and as we back up and we're looking at the end of the shaft, it's slowly rotating more and more until we get to B. Then at B, it's got an applied load that's going the other direction. Okay, the applied load in the other direction results in that internal torque of 170 Newton meters. Over the length of that, it's going to slowly start twisting it back the other way, right? So as it slowly starts twisting it back the other way, right, this would be at A, this would be at B, and this would be at C. This is the angular rotation from B to C, right? The angular rotation 2, or the shaft 2. Okay. So we stood in it at A, it hasn't rotated. As we back up, the internal torque, right, is slowly rotating it until we get to the end of the first shaft. Then we get to the end of the first shaft, and we continue to back up. The torque's going the opposite direction. So it starts overcoming the rotation that we had from A to B, because it has a greater magnitude, right? It's 4.58 times 10 to the negative third. So finally, we're going to get to point C. So the deflection at C relative to A is this deflection, right? A to C. From A to B, we went one direction. B to C, we overcame what we did from A to B, went back the other way to C, and now we really want to know what's that difference between A and C. So deflection C relative to A, deflection of rod 1 plus rod 2. So that's negative 1.676 plus 4.581, all of this times 10 to the negative third, or we get 2.905 times 10 to the negative third radians. Looks like a lot of shit, huh? Does that make sense? Any questions? A little bit tedious there, but you just kind of walk yourself from one end to the other.
Why did we skip over pulley B?
Pulley B?
Yeah.
We didn't skip over it. So even though it applies a torque of 260 Newton meters here, because we have a restraining torque at A and C, the actual torques that these shafts see is only the internal torques that we calculate.
Okay.
Does that make sense? So as we start at A, it doesn't. If we start at A, okay, and we're walking backwards, the shaft between A and B only sees the internal torque in that shaft, which is the torque applied at A, okay? When we get to B, its magnitude is significant, right, 260. But it has to first overcome the internal torque in A in shaft 1, okay, because it's acting in the opposite direction. So really, it's only applying 170 Newton meters at this location. And the shaft rotation and displacement is based on a torque over a given length. And so at an instantaneous location here, that applied torque is really not doing anything to the deflection of the shaft. It's the fact that it's over a length that we accumulate this rotation, right? I mean, like the green stripes here, right? As you twist that, it's got a linear rotation to it. And so here, it sees that there's no rotation. But out here, as we travel along the shaft, you continue to build up those small amounts of rotation until you have a final rotation at the end. And so we really wanted to know what's going on between A to B and then B to C. Yes?
So it kind of looks like a localized moment in like a beam shear moment diagram. How like a localized moment at a point on a beam causes
Gives you a jump.
Yeah.
Yep. So it's like an instantaneous jump, which is happening right here. As far as the shafts are concerned, they don't care what the applied torque is. They care what's happening internal to them, which is a function of the overall system and how those torques are being resolved throughout the entire system, which in this case are 2 pulleys on either side. But we could have a series of 5 or 6 of these pulleys. Some are contributing, some are taking away, and it's all based on the directions of those applied torques. Great questions. Anything else? Okay. Now we're going to get to gears, which I'm sure you METs are going to be stoked about. Okay. And more importantly, we're going to look at gears and torsional assemblies because we're still talking about torsion. Okay. Gears are incredibly powerful tools, okay, in design. Allow us to change direction, change force, okay, speed, things like that. So really we're trying to transmit torque and rotation. And I guess I will clarify that in this class, we're going to be working with, we're going to base on fixed gear ratios. Okay. If you look at a constant velocity transmission, which are in some cars, or snowmobiles is one of the most predominant ones, but four-wheelers now, right? Automatic motorcycles and things like that, okay? They work on a variable gear ratio, okay? Constantly changing depending on the torque that's applied. It's a fascinating thing. But yep. Or they have chains too, which is crazy, but they do have chains that do that same thing. But yeah, essentially varying an infinitely fluctuating gear ratio between two ratios that allows you to make one smaller and one larger depending on what the applied torque is. And based on the speed. So if we look at this thing, I think my buttons keep fucking this up. Look at torque transmission in a system in equilibrium. That's what we have here, which is really this, right? If we looked at what's going on in that diagram. A little bit straighter gears than that, but this is effectively what we have. We looked at the end of this, right? We've got two gears that are touching each other, okay? One is larger than the other, okay? One has a radius RB, the other one has a radius R sub A, right? This is gear B, and this is gear A. So if we had a gear system like this, we have gear B driving gear A or vice versa, right? They're interlocked with the teeth in the gears. Okay? And if we separated these two gears and drew a free body diagram, this is what the diagram would look like, right? This was in static equilibrium, right? The gears didn't move. So if you were holding your hand on each end of these, okay, and you're pushing on yourself each way, okay, and those forces were equal, so the gears weren't moving, the force that was between the two gears is equal, right? F equals F. So if we sum the moments at gear A about our x-axis, is that a helicopter? Anybody love helicopters as much as me? And they are incredible. They are incredible. Has anyone ridden in a helicopter? God, I envy you. I tell my wife every year, I'm like, best present in the world is just take me on a helicopter ride, and I've yet to get one, so maybe that'll end soon, I guess. So, summing the moments about gear A, okay, about the x-axis, we're going to set that equal to 0. Well, we've got the torque in the shaft 1, right, T1. It's acting in the x-axis, so we're going to say that it's positive. Then we've got this force, F, right? And its moment arm is the gear radius A, right? The radius of gear A. And we've got this force, okay, F. And based on the right-hand rule, right? You curl your fingers in the direction of the force about its moment arm. We've got our thumb pointing backwards from our assumed positive coordinate, right? So it's rotating A backwards. If it's rotating A backwards, our thumb's pointing off to the left. That's in the negative coordinate direction from what we assumed is positive. So we get a negative F times RA, okay? This tells us that T1, right, the torque in has to equal the torque out. So the torque that we're applying in the shaft of gear A has to equal the torque applied based on the force that we're applying between gear A and B, right? F. So the forces have to be the same. Well, if we look at solving this for the force, we're going to say the force that we can apply at the edge of our gear, okay, is the torque applied to the gear divided by the radius of the gear. So as the gear gets larger, that force we can apply goes down. Kind of makes sense, right? We have a bigger moment arm, we have less force. Okay? Does that make sense? I think it makes sense. Well, if we do that same thing, let's do that same thing at B and do it about this x prime axis. We're going to say that equals a 0. We're going to get negative T2 minus F times RB. Everybody get the signs there? T2, outward normal, okay? It's facing in the left direction. Well, it's opposite our assumed positive x prime axis, right? So it's negative. Then our force, F, right-hand rule, if we curl our fingers in the direction of that force around that blue gear, our thumb's going to be pointing opposite of our assumed positive coordinate. That's also negative, so we get two negatives. So we have T2 equals negative F RB. Well, I'm going to substitute. If that's even how you spell substitute. It doesn't seem right, but it must be. F T1 divided by RA. I want to get an expression for T1 in terms of T2. So if we apply a torque here, how does this torque applied relate to the torque that comes out on the other end? So I use the force that I solved for, summing the moments about gear A. I'm going to plug it back in. So then I end up with this expression T2 equals minus T1 RB over RA. What are some things to take away from this? Well, if you have a gear system with gears that are touching each other, okay, in this fashion, there's all sorts of different gears like worm gears, screw gears, things like that. We're not going to talk about that in this class, okay? Just fixed gear ratios. If we look at this equation, T1 and T2 have opposite signs. Right? If you apply a torque in one direction, in one gear, say gear A, it's going to be applying a torque in the other direction coming out of gear B. Also, T2 and T1 are related by RB over RA. This is our gear ratio. Pretty cool, right? So if you're given one torque, you know what the gear sizing is, you can figure out the torque on the other end. Right? A lot of times this can be given in a number of different ways. So gear sizes. Can be communicated by different methods. Okay, we've got radius, which which is how we did it. Sometimes it can be based on diameter. Sometimes it can be based on number of teeth. Right? Mountain biking is a prime example of that. Okay? Changing the teeth on your drive gear, right, is going to change the gearing ratio for all of the gears in the ring set, right? Dirt biking, same thing. You're running a transmission, but in the end, you've got this sprocket that's running another sprocket on the tire, right? And it's connected with a chain, which we'll talk about that in a second. Okay? But there's a gear ratio there, right? The small one's driving the large one. So we got RB over RA. Well, for diameters, it's 2RB, right, over 2RA. That's the same as saying diameter B over the diameter of A. That's the same as saying number of teeth. B over the number of teeth of A. And all of this is your gear ratio. Yes?
So then it's a unitless gear ratio, it's a unitless, it doesn't matter.
Yep, unitless. It's just a proportion of size. Well, let's look at a couple different setups for this, okay? So this is like the example we just did where we had RA and RB, right? 2 gears. This is a flywheel on the back of an engine, okay, or a small motor. This would be what's driving it with your starter, okay? You go and turn the key in your car, it turns on a solenoid that throws this starter into gear, throws this gear out and starts turning the engine, okay? As you can imagine, the starter motor is not gonna have a lot of juice to it, right? So you want the torque applied there to be able to expend like the torque applied on the motor, right? Give it more power. In order to do that, you give it a small gear so that the force applied here, right, over the moment arm is small, but now you have this force applied over a large moment arm, so you're applying a huge torque. So the flywheel is large. So we found out from before, right, with this setup, we've got T1 or T2 equals minus T1 RB over RA. Right? If this was A and this is B. Right? So if this was A, our starter gear, this is B, our flywheel. I'm not going to do that yet. This is essentially saying the torque at B equals minus the torque at A times the radius of gear B over the radius of gear A. Well, when we look at this setup, if we assume they are no longer in static equilibrium, and there's some forces involved, right, where we have rotation, right, this thing starts moving, okay, we're going to have, or we have an applied torque, right, which would then deform this rotationally, right, based on our equation, T times L divided by G times J. Well, looking at the rotations of this setup, if B rotates counterclockwise, A is going to rotate clockwise, right? This would be R sub A. This is R sub B. So we can also utilize our gear ratios to relate the speed and rotation of our gears, right? Or our shafts, whatever's attached to this is going to be also relative to this gear. So we can say that the rotation at B now is the rotation at A. In this case, it's R sub A over R sub B. In this derivation, we're talking about displacement. So if we we know that the displacement where these two gears meet has to be the same, right? And so that rotation or that motion at the end of this is our displaced angle times our radius. So in our case, the displacement of B, or the rotation at B, times its radius has to equal the rotation at A times its radius, right? Well, if you divide by rotation at B on the left, you get this expression that the rotation at B is going to be the rotation at A times this gear ratio of the rotation at A, or the radius of A over the radius of B. Similarly, that same concept holds true for rotational speed. Call it omega B equals minus omega A times R sub A over R sub B. What are you doing? So before we leave, I would just write gear ratios.
Were A and B supposed to switch being on top of?
Yes. Yes. So they also dictate angular rotation, right? That's our rotation equation. Phi sub A equals negative our gear ratio times phi sub B. Similarly, rotational speed A equals minus gear ratio times the rotation of B. And yeah, this is because what I just mentioned, the reason why this gear ratio flips is because if you set, right, if you have these two gears sitting next to each other, and this gear B rotates, say the flywheel rotates a little bit, the distance that this rotates here has to be the same distance that gear A rotates, right? And the distance that those two rotate is proportional to, right, phi sub B R sub B equals negative phi sub A R sub A. And so when you divide by R sub B, you get this expression here. Because for very small, it's a small angle theorem. And for very small angles, this distance, the arc length, is the radius times the angle. Does that answer your question? And speed is the same. I mean, if these guys are like hauling ass moving, the speed right here has to be the same between the two gears. Otherwise, you're going to be skipping.